Welcome to section 7.5, Logarithmic Functions. At the end of this section, you should be able to answer these questions. What is the general equation of a logarithmic function? What is the relationship between a logarithmic function and an exponential function? What are the key characteristics of a logarithmic graph? What is the numerical pattern associated with logarithmic functions? And finally, how do we solve for a particular logarithmic function given data or a graph? Well, let's start with the general equation. Here, the general equation of a logarithmic function in its untranslated form is y equals a plus b log base c of x. A, b, and c are constants. B can't be equal to 0, because then you would just have y equals a. C has to be greater than 0. To raise something to a power over particular values of x, we need to use positive bases. C can't be equal to 1. A base of 1 would result in a constant value of y equals 1. If we are going to transform the function, then our equation looks like this. Y equals a plus b log base c of x minus d. A is going to be our vertical translation. B is our vertical dilation. And d is the horizontal translation. Here I've graphed 5 different logarithmic functions. Log base 2 of x, log base 3 of x, log base 4 of x, log base 5 of x, and y equals log x, or base 10 of x. Let's look at the different graphs and figure out how we can determine which of the graphs is associated with which of these equations. Alright, first of all, let's look at and notice that each of these graphs has certain characteristics in common. First of all, they're all increasing as long as x is greater than 0 and have no values for x less than or equal to 0. And finally, they all go through the same point here. They all go through 1, 0. Now let's look at how they differ. You'll notice that if I look at each of these possible graphs, for instance, y equals log base 2 of x, I can rewrite this as an exponential function. So 2 to the y equals x. And if I want to know what happens when y equals 1, 2 to the first is going to be 2. So when x is 2, we are going through y equals 1. If my graph is y equals log base 2 of x. If my graph is y equals log base 3 of x, well, log base 3 of 3 is equal to 1, because 3 to the first power is going to result in 3. So log base 3 of x has the point 3, 1, which means that log base 4 of x should have the point 4, 1, and log base 5 should have the point 5, 1, and log base 10 should have the point 10, 1. So if I look at these different graphs, I can see that at 2, 1, that's my green graph, which would mean that log base 2 is the green graph. The graph that goes through the point 3, 1 is this purple one. So log base 3 of x is going to be the purple. And we can see that the graph that goes through 4, 1 is the blue. And the orange goes through 5, 1, so that's log base 5. And finally, the one that goes through 10, 1 is log x. Let's look at what happens when we determine the inverse of the natural log function. If I start with the equation y equals log of x. So let's use the common log function. And I'm trying to determine the inverse. So this is f. So the inverse of f would, the first thing we would do is switch our x's and y's. So x equals the log of y. Now, if I burp that equation, solve for y, then in my inverse, y is equal to base 10 to the x. So if my original equation is a logarithm, the inverse of that equation is an exponential equation. Logarithms are inverses of exponential equations and vice versa. Alright, so let's see what we can do with these logarithms. First of all, we've just looked at the patterns for linear equations, power functions, exponential functions, and quadratic. Since we now know that logarithms are inverses of exponential equations, and we know that exponential equations have an add multiply what do you think multiply the pattern will be for a logarithmic equation? Alright, well, I hope you guessed that since exponential is add multiply, logarithms will be multiply add. Here's an example of some data points from a logarithmic function. If I look at my pattern, here I'm going to be multiplying by 3 each time. And the result is I increase by 1 each time for my y values. Alright, so how would that work in a problem? Well, here we are told that we have a logarithmic function, and we're given a couple of data points. F of 3 equals 7, and f of x, or f of 6, equals 10. So without finding the particular equation, can I find f of 12 and f of 24? Well, if I set up a table of x and y values, I should be able to determine what the pattern is for this particular logarithmic function. So since I know it's a multiply add, I look and I see here I multiplied by 2, and when I multiplied by 2, my y values increased by 3. So if I want to find 12, that's another multiply by 2, which means I should add 3 again, which would give me 13. And then if I multiply by 2 again, I'll end up with that 24, which means I should end up with, wait for it, that's right, 16. So let's just double check that. 13 and 16. Good. Alright, so now we want to find the particular equation algebraically using natural logarithms. Alright, so again, we take the same approach we took with all our other types of functions. We start with the general form, which is y equals a plus b, and here they're telling us to use natural logs, so ln of x. and I plug in the two given values from the first part of the problem. So y is going to be 7 when x is 3. And then y is going to be 10 when x is 6. All right. So here we take it and we need to solve for a and b. And we have two equations with two unknowns. Once again, we have the choice of linear, or we have the choice of elimination or substitution. If I subtract, it looks like I could eliminate a quickly. So negative, if I subtract on both sides, negative 3 equals b natural log 3 minus b natural log 6. All right, here I can factor out a b, so I have negative 3 equals b times the natural log of 3 minus the natural log of 6. I can apply my properties of logs and say that that is b times the natural log of 3 divided by 6. Subtraction results in a quotient. So negative 3 equals b times the natural log of 1/2, which tells me that b is negative 3 over the natural log of 1/2. So let's pull out our calculators here and figure out what b is equal to. So b was equal to negative 3 divided by the natural log of 1/2. Whoops. And that turns out to be 4.3281. So b is equal to 4.3281, and we're going to use that information to solve for a. So we'll take our first equation here, and we'll replace b with its value. So 7 equals a plus 4.3281 times the natural log of 3. So a is going to be equal to 7 minus 4.3281 times the natural log of 3. Once again, we call on our calculator. So we have 7 minus this value times the natural log of 3. And that turns out to be 2.245. So a is equal to 2.245. And if we're going to check that, let's see what we've got here. Yes, f of x is 2.245 plus 4.3280. Success. Alright, so let's recap. What is the general equation of a logarithmic function? Well, it's right here. Y equals a plus b log base c of x. What is the relationship between a logarithmic function and an exponential function? Well, we saw when we looked at the graphs and discussed them that the logarithmic function is the inverse of the exponential function. What are the key characteristics of a logarithmic graph? Well, if we look at those graphs, we can see that they're all increasing for x greater than 0. They're concave down. They all go through the point 1, 0. And then they will also go through the point of the base, 1. What is the numerical pattern associated with logarithmic functions? Well, we saw that the numerical pattern was multiply, add, which makes sense since the exponential function is add, multiply. And how do we solve for a particular logarithmic function given data or a graph? The same way we solved for all our other functions, by using the general equation and plugging in values for x and y to get a system of equations with the appropriate number of unknowns.